name is Lucas Garfield. I'm the director here at the European Bryan Research Engineering office in Brno, Czech Republic. Today, what we're going to be talking about, basically, we're just going to give you I'm going to give you a really broad overview of 4 different ways that you can perform carbon capture, simulate carbon capture processes in ProMax. We're going to talk a bit about how you select the correct method, and then specifically we're going to talk about how you simulate carbon capture with chemical absorption. Specifically, we're going to discuss using amines today, and even more specifically, we're going to talk about using an MDEA piperazine blend. You'll sometimes hear that referred to as activated MDEA. So we're going to show you how that works. And then we're going to show you how to simulate carbon capture with physical solvents as well. That'll probably take up the bulk of most of what we talk about today, but then we'll also touch briefly on a very interesting technology. I don't think it's very widespread, but low temperature distillation. So that's sometimes called the Ryan-Holmes process. So what do you actually, if we have these choices, what's the appropriate choice? That's really going to depend on how much carbon you have to remove and what the ultimate specification that you need to meet is. If you consider, for instance, pipeline gas versus liquefied natural gas, the difference in minimum CO2 content, or the difference in the maximum CO2 content, is huge. For a pipeline gas, you might have to meet a 2% on volume basis specification, whereas with LNG, liquefied natural gas, typically you need to get down to a ppm level. So that's certainly going to affect what you use. And the other thing that's going to affect what you use is how much CO2 you have in your feed, and perhaps even more so, what the partial pressure of the CO2 in your feed gas is. So we've got a pretty interesting plot here that kind of gives you some ideas of what process might be viable depending on both what the partial pressure of CO2 in your feed gas is, that's on the x-axis or the y-axis, and then what partial pressure you need to achieve in your product, and that's on the x-axis. And this is a little bit of a complicated plot at first. Keep in mind that both axes here are actually the same. They're in units, they're in terms of the partial pressure of your acid gases. And we're including H2S and CO2 because those are usually captured together, but for this lecture, we're really just concerned about the CO2. And notice that both axes are on a log-log scale, but the x-axis starts at 0.01 and goes up to 10, whereas the y-axis, it's got different starting and ending point. It goes from 1 to 1,000. So you see that line in the lower right-hand corner from that starts at 1. That's actually the parity line, right? That's where this is the same. And so we don't need treating if we're below that line. But if we're above that line, we do need treating. And what we see is that if we need to achieve a really, really low final partial pressure of CO2 in our product, and the feed partial pressure of CO2 is low, we'll probably need to use an amine. And if we're at a very high partial pressure of CO2 in our feed, that's when we can start thinking about using physical solvents. So that's really going to be the big that's going to be really the big thing that helps us determine, do we want to use a chemical solvent like an amine or a physical solvent? Physical solvents, because they rely purely on physical absorption, they really only work at high CO2 partial pressures, which you may not have. If you think about carbon capture from something like flue gas, that's at nearly atmospheric pressure. And so in that case, certainly a physical solvent wouldn't work. You would need to use a chemical solvent like an amine. Some other questions that we need to ask are, can any of the other components that are present co-absorb into the solvents? So again, with physical solvents, heavy hydrocarbons tend to be very soluble in physical solvents, and that's something that we're going to have to think about. There are some ways to mitigate that, and we'll actually see that when we open the simulation for DEPG, one of the physical solvents we'll discuss today. But co-absorption of hydrocarbons is something to think about. And, you know, the source of the gas might influence this. For instance, if you've got a natural gas stream is definitely going to contain heavy hydrocarbons, right? If you have something like syngas, on the other hand, then you probably don't have heavy hydrocarbons, and so maybe that's not such a concern. The other question is, how pure do you need the CO2? If you need really high purity CO2, then what you may want to actually look into is having either a membrane or cryogenic fractionation. Those two processes will give you a very, very high purity CO2. And the difference between these two processes really has to do with the final pressure. With membranes work entirely based on a pressure drop. And so the CO2, it's going to be at a low pressure. Whereas with cryogenic fractionation, you can produce a high pressure CO2 product. But let's just take a moment and review some of the chemistry behind the chemical solvents. So this is specifically going to be carbon capture with an amine. And when we say chemical solvents and chemical absorption, what we're really trying to get across is this idea that there are going to be chemical reactions that are occurring during the absorption process. The specific chemistry, it's going to be this acid-base chemistry, and we're going to have ionic species. And so that's something that we've got to think about, and I'll show you what the implications in the chemistry are in just a moment. But one of the nice things about this is that because we're using chemistry to capture the carbon dioxide, this process works at both high and low pressures. Chemical solvents, amines, can also get us down to very, very low levels of acid gases, so we can get to ppm levels. And just broadly speaking, there are really three classes of amines that we talk about, and it depends, the class of amine depends on how many hydrogen, or how many substitutions you have around the central nitrogen atom. All of the amines basically start with almost like an ammonia molecule, right? And you can see that primary amines have a single substitution, secondary amines have 2 substitutions, and tertiary amines have 3 substitutions. Now, what that substitution actually is going to depend on the amine that we're using. There are different substitutions, but alcohol substitutions are very common. For instance, a very common primary amine is MDEA. That's also used sometimes for carbon capture. And MEA is monoethanol amine, right? So it has a single ethanol substitution. A common secondary amine would be something like DEA. DEA is diethanol amine. So the 2 substitutions for DEA are still both ethanol groups. And then a common tertiary amine that we use, which we'll be talking about today, is MDEA, and that's methyl diethanol amine. So that actually has a methyl substitution and 2 ethanol substitutions. Now, we're not going to get deep into the reaction mechanism today, but what I want to just kind of suggest to you is that the tertiary amines are going to behave quite differently when it comes to carbon capture than the primary and secondary amines. And I'm just going to suggest that the reason for that does have to do with the mechanism, and that the mechanism has to do with the fact that primary and secondary amines have that proton, and tertiary amines don't. We'll talk about that more in just a second. And I know that this is a lecture about carbon capture, but because we use these amines so commonly for co-absorption of H2S, let's just take a look really quickly at how H2S is actually absorbed. H2S dissolves in solution first. That's the first reaction that we see there. H2S dissociates into the bisulfide ion, HS minus, and a proton, H plus. And then that bisulfide ion can further dissociate into the sulfide ion, S2 minus, and a proton. So the top two reactions, those both generate protons as products. And those protons can react with the ammonia, the amine, which is a base, and form protonated amine as a product. And so that's what you see on the very bottom. These reactions all occur very, very quickly. For CO2, the reaction chemistry is a little bit more complicated. CO2 can react directly with water to form bicarbonate and a proton. That's the first reaction. CO2 can also react directly with an amine to form the carbamate complex and a proton. That's the second reaction. And then if you look at the third reaction, the bicarbonate from the first reaction, that can react directly with an amine as well to form carbamate again. The key thing that we have to remember here is that that first reaction, the kinetics of the first reaction, the CO2 reacting with water to form bicarbonate, that's a relatively slow reaction. And when I say relatively slow, what I mean is that if we're thinking about the time scales that we have in a typical trade absorber, where the residence time on a tray is on the order of 1 or 2 seconds. This reaction is slow in that context. Now, there is a corresponding fast reaction. CO2, the second reaction, CO2 can react directly with amine. But here's the interesting thing. The second reaction does not occur when we have a tertiary amine like MDEA. So MDEA, the absorption of CO2 by MDEA, methyl diethanolamine, it's limited to that first slow reaction. And that's going to have some big implications for carbon capture, as we'll see in a minute. So we kind of discussed what the molecules actually look like a moment ago. And here again are just some pictures. So MEA is a primary amine. So that's monoethanolamine. Diglycolamine, DGA, that's another primary amine that's used sometimes. DEA is a secondary amine. Methyl diethanolamine, that's the one we're going to be using today. It's a very popular amine. We'll talk about why in just a moment. And then we've also got this last one here, DEPA, diisopropanolamine. That's actually a secondary amine, but it tends to behave as if it were a tertiary amine. And the reason for that is typically attributed to the steric hindrance. It's got these two big bulky isopropyl groups, and they kind of occlude that proton. And so remember how we said that the slow CO2 absorption is due to the fact that we can't go through the fast route because the mechanism won't work without the proton? Well, the steric hindrance from the DEPA kind of gives us an effect that's similar to that, even though the proton is present. So I've mentioned a few times that MDEA is a popular amine, and the reason for that is simple. It's a tertiary amine, which means that it's less aggressive and less corrosive. So that's one reason that it's popular. The primary amines like MEA, they tend to be very, very corrosive, and so they have to be used at, especially when they're loaded, especially the loaded solvent, it tends to be very corrosive. So you have to operate them at low loadings. MDEA can actually be operated at much higher loadings because it's not as corrosive. If you think about what that means that there's less water. And because this is a regenerative process where we have to regenerate the solvent, the lower the circulation rate, the lower the reboiler duty. MDEA also has a low heat of reaction with CO2. It's easier to regenerate. And one of the reasons that it's used is because it can selectively remove H2S and let CO2 slip out of the top. This can be a big benefit for us if we're trying to do something like produce gas for a pipeline, where we need to remove H2S down to ppm levels and we only need to meet something like 2% CO2 specification. But if our goal is to really, really get a carbon-free stream like we would need for LNG liquefaction, that presents a problem. Now, we can overcome that problem by using a blended solvent. So you can actually mix multiple amines together and kind of get some of the best properties of each. You can take MDEA, for instance, and mix it with another amine that's perhaps a little bit more aggressive. You'll keep most of the benefits of MDEA, but you'll also get the benefits of whatever you've added in. And the key example here is piperazine. This is the molecule that we really want to talk about today. Piperazine, when it's added to an MDEA solution, hugely increases CO2 pickup. It's typically used at a low concentration, about 1 to 5 weight percent. And one thing you do have to watch out for is that it is more volatile than MDEA, so losses can be high. A lot of times you'll need like a water wash on your absorber to help minimize losses. And if you look at the molecule, you can see that it's basically, it's like an amine. It's this ring structure. It's actually got 2 nitrogens. And each nitrogen only has 2 substitutions. So it's kind of like a secondary amine. And in fact, it's like you've got 2 secondary amines in one molecule. So this is really powerful. This is really going to help us remove CO2. So what we'll do now, I've got a simulation up here. And we can just take a look at what simulating a generic MDEA process would look like, and then we'll also take a look at what happens when we add some piperazine to the mix. So I've got ProMax open, and the first thing I've got to make sure that I do, if I'm simulating one of these processes, I need to make sure that I have the correct environment selected. When you simulate an amine sweetening process, you're going to be absorbing these acid gases with a basic solution that's primarily water. So there's a couple things going on. We need to make sure that we've got a property package that will work for that. And what that means is we need an electrolytic property package that allows species like carbon dioxide or hydrogen sulfide to dissociate and participate in that acid-base chemistry. So if I click here on active environment, you'll see that the environment that I've selected for this is amine sweetening PR. PR stands for Peng-Robinson. We're going to use the Peng-Robinson equation of state to calculate the properties of the vapor, but all of the properties of the liquid are going to be calculated using our proprietary electrolytic extended long-range package. So that's the first thing that you need to do if you're simulating one of these processes. Now, if you've never seen this process before, I'll just kind of give you a really brief overview. And we've got kind of 2 units mashed together on this single flow sheet here because we want to just show you one that's with generic MDEA. That's going to be the one on the bottom. And then one that's MDEA that has just a little bit of piperazine added in. That's the one on the top. So we have the same feed gas coming in, and we just split it 50-50 to each unit. Let's take a look at the composition of that feed gas. I'm going to open that up. Change my units up here to kilojoule bar, and let's just go to the composition and see what we've got. So this is about 90% methane, and then we've got 3.5% carbon dioxide and about 50 ppm of H2S. Okay, so 3.5% CO2, 50 ppm H2S. Now, in terms of the actual process, what we do is we send that sour gas to our amine absorber. We're going to operate the amine absorber at a high pressure. That's going to favor physical absorption, which has to occur before we can have chemical absorption. But then after physical absorption occurs, dissociation is going to occur. Those reactions we showed you occur, and the amine is going to capture the CO2. So we'll end up with a rich amine. So the rich amine is going to be the amine that includes the captured CO2. And we'll send that to a regenerator, which is basically just a stripping column. It does have a little bit of reflux, but that's just to help keep our losses down. It's really a stripper. And then we're going to use heat in the form of, in this case, steam. We use steam to power our reboiler and drive the CO2 out of solution. And this vent gas, that's where our CO2 is going to end up. So that's the basic process. One thing that you've got to make sure you do if you simulate one of these is include those CO2 kinetics. If you think about it, this is actually a reactive column, right? I mean, we need to consider the kinetics of the CO2 absorption. And luckily, ProMax does that all for you automatically. You've just got to make a couple of changes to the settings. If I open the absorber, you can see here under process data that I've selected the T-Suite absorber stripper column type. T-Suite is kind of the name for one of our old legacy products, and we've kept it throughout the years. And what this really means, it stands for trace sweetening, and what this really means is that we're considering those CO2 absorption kinetics. So once we've got that in, we can consider our CO2 absorption. And let's just take a look at what the performance is like for pure MDEA. Again, the feed was about 3.5% CO2. And if I open the sweet gas here, and I look at the composition, I see that I've got about 1.3% CO2 in the overhead. So I've captured roughly 2/3 of it. I could actually, if I wanted to, I could open the column. I've got this convenient recoveries tab here in the column. And if I look at that, I can see that my recovery of carbon dioxide is about 63% into the rich amine. Now, this is circulating pure MDEA, and the way that we set that up is in this makeup blowdown block. If I open the makeup blowdown block and I go to the process data tab, you can see here that we've set the target outlet composition to 50% MDEA. We've also set the bulk composition to 100% water. Basically what this block does for us is it says control the circulation rate at 50 weight percent MDEA. If you need to add more MDEA to get it to 50%, add some. If you need to purge a little bit, purge. And it takes care of that makeup and purge for us automatically. If I scroll up to my MDEA piperazine model, and I open the makeup block here, you'll see it's configured just a little bit differently. Under process data here, we've added 1% piperazine to our target outlet composition. So now we've got 50 weight percent MDEA and 1% piperazine. And again, we've got the same feed with about 3.5% CO2. Let's take a look at our sweet gas now. So our CO2 has now gone down to 26 ppm. It was 1.3% previously. So 1% weight piperazine has taken our CO2 content in the sweet gas from 1.3% to almost nothing, down to the ppm level. So that's the power of piperazine with MDEA. And just a couple of things to think about when you do add piperazine to a process. Piperazine does have a fairly high heat of reaction with CO2. So it's really good to go ahead and check the temperatures in the column. Let's compare the two columns' temperature profiles. If I open the MDEA absorber here, I'll show you guys a trick. There's a nice feature I like. If I click up here on window, I can click pop-up active view. And that gives me a copy of the project viewer. So this, and that's going to let me put these two plots side by side. So here I've got the temperature profile for the pure MDEA absorber. And then let me also open the temperature plot for the absorber with piperazine. So you can see that for the pure MDEA absorber, the highest temperature that we reach in the column is about 63 degrees Celsius. Whereas now with that piperazine, we're getting all the way up to 75 degrees Celsius. So there's a big difference. So that's something that you definitely want to check. And then the other thing you've got to be careful about when you add piperazine is that it's a little bit more difficult to regenerate. Now, in this simulation, we've set up both strippers reboilers to use steam. And in fact, we're using the same amount of steam. So the reboilers, they have the exact same duty. If I hover over this duty stream, you'll see that it's about 3,046 kilowatts. And if I hover over this duty stream, you'll see the same number, 3,046 kilowatts. So just one thing to be careful of, the lean loading here in the piperazine process is going to be higher than it is here. Why is that important? Well, we need to think about corrosion and the materials that we're using. One of the places that corrosion can be a concern, for instance, is in the piping around the reboiler. And one of the things that we tend to look at is what's the CO2 content of the vapor in the reboiler. Basically, the piperazine, it's harder to regenerate, and it's going to tend to pull the CO2 down the regenerator. If I were to open this stream 33, this overhead from the generic MDEA, the pure MDEA case, if I look at the composition, I see that that's about 0.4% CO2, and that's fine. A very conservative recommendation is to stay below about 1%. But if I go and I check what it's like in the piperazine case in stream 13, the composition is about 0.76%. So we're still okay. We're still below that 1% rule of thumb, but the CO2 content is starting to creep up. So that's something that we want to make sure we think about. But that's really it. That's it for the solvent process. It's very simple, very easy to simulate in ProMax. And the key for using MDEA piperazine, it really just comes down to setting up the desired composition here in the makeup block. And I accidentally disconnected that stream, but that's okay. We're done with this anyway. Now, I didn't really go very far into depth about the amine. And that's because this webinar is really just supposed to be a very broad survey of these 4 different technologies. But coming up throughout the rest of May and June, we're going to have a lot of sessions about simulating amine processes. So this Thursday, we're going to have simple MDEA sweetening. That'll be an exercise where you can actually, if you join, get some hands-on experience simulating an amine unit yourself. And then you see that in June, we're going to have online sessions where we do a comparison of different amines. We talk about simulating packed columns, and then we talk about all sorts of different flow configurations. All right, so let's talk about physical solvents next. Physical solvents are a lot simpler than chemical solvents because we don't really have any of those chemical reactions occurring. The absorption is purely on a physical basis. And what that means, again, like we talked about earlier with that plot at the very beginning, it means that we need to have high partial pressures of CO2 for the absorption to work. We've also got to be careful because the physical solvents, they tend to have strong affinities for heavy hydrocarbons, and that can be something that's not useful to us, that's not desirable. And another thing that they sometimes those affinities for other species are useful though, because physical solvents will tend to absorb species like CS2, COS, and mercaptans, and that, if those species are present, that can be very beneficial. So you can see we've got a picture of a DEPG unit here, and it looks very, very similar to an amine sweetening unit. You notice the big difference is that we've got these 3 different flashes. And the first flash actually has a compressor that recycles it back to the column. And the reason that we do this is because you can actually do a huge amount of regeneration with physical solvents simply by dropping them to low pressures. With amines, dropping from a high to low pressure doesn't really tend to regenerate very much because the acidic species are held onto chemically by the base. But with physical solvents, just dropping to a low pressure will really get rid of a lot of the species that have absorbed. And so with DEPG, what we do is we have this high pressure flash, and that's going to help us recover some of those heavy hydrocarbons that absorbed. And basically what we want to do is we want to balance, capturing CO2 versus having this kind of high pressure regenerative flash that releases some of the hydrocarbons. So we'll take a look at that in a minute in an actual simulation. But just to give you an idea of some of the different physical solvents that you can simulate in ProMax, you can simulate DEPG, that's dimethyl ethers of polyethylene glycol. This molecule will remove both H2S and CO2. It also removes mercaptans, hydrogen cyanide, and water. And it's marketed as Selexol, most commonly is what I've seen it as. NMP is another physical solvent that you can simulate in ProMax. It's selective towards H2S, and it has a high vapor pressure, so you need to add a water wash. And this is sometimes seen as Purosol by Lurgi. Methanol can be used for capturing H2S, CO2, and other species. It's very aggressive. It's not particularly selective towards CO2 or H2S. And this one's marketed as Rectisol or Ifpexol. And then finally, we've got propylene carbonate. And propylene carbonate is very good for bulk CO2 removal, preferably when there's no H2S present. And this is marketed by Fluor. So the physical solvents, again, because they don't have any chemical bonds, they're very easy to regenerate. And there are a couple of different options for regeneration. You can sometimes just do a flash and, again, regenerate them just by flashing down to low pressure. You can add stripping gas if you have something available. You can generate your own stripping gas with a reboiler, or you can use a combination of these techniques. So let me just show you really quickly what one of these would look like. And I've got a DEPG unit here, and we'll just take a look at a couple of things. You can see that this DEPG unit, it's a little bit simpler than the one that I had on the slide. And it looks a lot like an amine sweetening unit, right? We have an absorber, we have a regenerator, and the only difference is that we have this kind of compressor on our rich flash. So let's take a look at what's coming in. Our sour feed in this case, if I open it, this is actually, in this case, 15% CO2, 75% methane, and then the balance is kind of different hydrocarbons and nitrogen. The key thing here is that we're at 68.9 bar gauge, so we've got a lot of pressure, and that's going to mean that this physical solvent is viable. Now, to set this up, it's really straightforward, just like the amine unit. If I open up this makeup blowdown block and I go to the process data tab, you see that we're just circulating 98% DEPG. So in this case, we're not circulating, as in the case of the amine, a mixture of water and solvent. Here, we're just using the pure solvent. And one question that you should probably be asking about is, what property package should I use for this? If I go to my environment, you can see that I'm using an equation of state. So in this case, we're just using Peng-Robinson. But we're using a special version of Peng-Robinson. We're using a version called Peng-Robinson Polar. This molecule, DEPG, it's a polar molecule, but we've got a special, and these polar molecules are not, their behavior is not predicted particularly well by the cubic equations of state. But we've got a proprietary model, Peng-Robinson Polar, and we also have an SRK version, SRK Polar, that does a very, very, very good job simulating these molecules. So all of the molecules that I just showed you, with the exception of the Fluor solvent, can be simulated using this polar property package. And then if we take a look at the performance of the unit, you can see that we're achieving about 1.75% CO2 in the overhead. And if I open up the absorber and we look at what the recovery is, I can go to process data here, and we can go to recoveries. You can see that we're recovering about 90% of the CO2. Now, also, do look at the recoveries that we're getting for some of the heavier hydrocarbons. We're also recovering into stream 3, and stream 3 that's again our bottoms rich solvent stream. We're recovering almost all of, okay, the COS and the CS2, that's good, but we're also recovering almost all of these heavy hydrocarbons, which, perhaps is not desirable. If I look at what's happening in my stripper, if I open the stripper and I go to the process data tab and we check the recoveries in our stripper, stream 4 is now our overhead. And if I look at stream 4, I can see that all of those heavy hydrocarbons ultimately end up here. So that's something to think about, again, if you're using a process like this. You're going to ultimately end up with quite a few heavy hydrocarbons in your acid gas stream. And that's mitigated somewhat by using this flash. So what we do here is we actually flash down to about 0.7 bar gauge. You can see that on the pop-up. So very low pressure. And if I look at the composition of this flash, it's mostly CO2, but it is going to contain a lot of my hydrocarbons. So this flash and recycle is going to help me a little bit, but still we're gonna end up capturing lots and lots of hydrocarbons with this physical solvent process. But overall, it's a lot like simulating an amine unit. If you can simulate an amine unit, you can certainly simulate physical absorption. ProMax does a very, very good job with all of these. The key points to remember are you've just got to make sure you have the right property package. That's going to be the polar version of the equation of state. And then you set it up like you would any other simulation. All right, the next process that we're going to look at today is low temperature distillation. And this is actually a really interesting process. I don't think that there are too many of these plants out there. I know that there are at least 12 in the United States, and I'm not sure about outside of the United States. And this is sometimes called the Ryan-Holmes process. And the idea here is, imagine that we've got a stream of natural gas, and then we've got methane and carbon dioxide, and then ethane, propane, etc. What if we performed a distillation where methane was the light key and carbon dioxide was the heavy key? That would mean in a distillation column, the methane would leave through the top and the carbon dioxide would leave through the bottom, right? The question is, where does, in terms of relative volatilities, where does CO2 fit in? I'll just go ahead and tell you, propane is less volatile than CO2. So if methane is our light key and CO2 is our heavy key, propane is even heavier than CO2. But how does CO2 compare to ethane? Well, CO2 and ethane actually form an azeotrope when it comes to distillation. And the azeotrope occurs at about 66% CO2. And if you think about what that means, it means that CO2 is the light key up until about 66%, and then it switches and becomes the heavy key. So here's what here's that azeotrope. You can see the CO2-C2 azeotrope here. So that's going to be a problem for us. And if we want to actually perform this distillation and get this to work, practically it means that we're actually going to need to do an extractive distillation. So we'll add an additive to the process that breaks the azeotrope. And that's what you see with the dashed line. And just practically speaking, the additive that we're going to use to break the azeotrope, we're going to use butanes, butane plus, because they'll be available in the natural gas. We can generate them in situ from the process, and we can use those to break the azeotrope. So let's take a look at what this Ryan-Holmes process looks like. So I've got an example up here, and I've got some other columns. But first, I want to just focus on the demethanizer. Let's take a look at it. Let's take a look at our feed. Our feed's composition is a little bit different than in our previous examples. Here we've got about 60% CO2, so we've got a lot of CO2, and then the balance is methane, ethane, and some other hydrocarbons. Now, this is going to be a cryogenic process. We're going to need cold temperatures if we want to split methane from CO2. So we're going to come into the column at negative 51 degrees Celsius. You can see that here. And then what we'll do in the column if I open the column and I go to the specifications, the way we'll control this column, you can see I've got two active specifications. The first is the CO2 in the overheads. That's a specification I've set up, and I'm saying keep the CO2 in the overhead stream to 1.8%. And then I'm also saying keep the methane in the bottoms to 0.5%. So basically, I'm just doing this distillation here. If I look at the overhead, I'm at negative 90 degrees Celsius. So that's colder than the feed. And here's my question. Think about this. Can you anticipate there being a potential problem with operating at cryogenic temperatures when CO2 is present? What if dry ice forms? I mean, CO2 can solidify, right? If I open up the column, if you may have noticed if you were paying really close attention earlier, I've actually got some warnings down here in the column. I'm being told that the temperature of tray 1 and tray 2 are both below the solids formation temperature, the point at which dry ice would form. And so this is the first problem that we run into. Now, ProMax does an absolutely fantastic job of predicting solids formation. ProMax is always looking for potential solids in streams on every stage of distillation columns. And if you're simulating a pipeline, it's also looking at every increment in the pipeline. Here, it's detected that we've got dry ice on trays 1 and 2. So if we want to dig in a little bit further and figure out exactly what the temperature, the solids formation temperature is, we can actually create an analysis just like we would create in a stream on the stage. So if I click here on analyses, you can see that I have a freeze out analysis. I've created this just by clicking add analysis and choosing freeze out hydrate water dew point. You can see there are other analyses available for you to create on stages and columns as well. It's been created on stage 1, but I can create analyses on any stage that I want. And if I click solve, what I see is that the solids formation temperature, it's actually negative 73.6 degrees Celsius. And again, we're at about negative 90, so we're too cold. And what we're going to do to fix this problem, we're not going to adjust the temperatures or anything in the column. We're going to add our additive that we discussed earlier. So I've got this stream here, and I'll go ahead and zoom out and let you see the whole picture now. And the additive, if I open it up, is basically our butanes plus. In this case, actually pentanes plus, but this is going to be just pentane, hexane, and heptane. And if I go ahead and I add that to my distillation column and I resolve it, if I open the column back up, now there are no warnings about dry ice formation. The column is going to be operating at a warmer temperature now that I've got those heavy hydrocarbons. So if I hover over, for instance, the stream of my residue, it was at about negative 90 previously. Now it's at negative 72. So the whole system's warmed up. And the hydrate formation temperature has actually also decreased because I've got those heavies in there. If I go back to my analysis and I click solve, previously the solids formation temperature was at about negative 70. Now it's at negative 95. So my demethanizer is in a much better position now. And if I look at the performance I'm getting, if I open that up and I go to the recoveries, I see that I'm getting really good performance here. I'm recovering 99.4% of the CO2 into the bottoms and 97% of the methane into the overhead. But now what we want to do is we want to take this bottom stream. If I look, I still don't have pure CO2. I've got 60% CO2, but I've got all of these other species as well. So now I need to separate the CO2 from the rest of these other species. So that's just done in another column. So I've got this column here, the CO2 removal column. We operate that at the appropriate conditions, and what we end up with is a high pressure, high purity CO2 stream. So if I open this stream, you can see that we've ultimately got 93% CO2. We're going to take those heavy components and send them to this sweetening column. And then what we'll do in the sweetening column, we're calling it sweetening column because we do have some H2S. The H2S, it's all going to end up in the overhead, which is going to be something like LPG. And this LPG, if I look at that, it's got about 2% H2S, 2% CO2. So it's going to need to be sent to an LPG sweetening unit. And then we'll take our heavies and we'll just recycle those and use those as our additive in our two columns, both to break the azeotrope and to suppress the hydrate formation temperature. And then we've also got this purge stream. So we're producing an LPG product here, we're producing a natural gasoline product, we're producing a high purity, high pressure CO2 product, and residue gas that's basically pipeline ready. If I open that residue gas stream and I go to composition, it's really high purity methane. So this is a cool process. I don't know if you've seen it before. Like I said, it's not very common. I'm not sure how the economics of the process work, but it's pretty unique. It's pretty interesting. So perhaps it's a little bit less relevant than solvent-based processes, but it's kind of a fun thing to think about. All right. Last topic today, we're just going to briefly talk about our membranes. And I'm just going to show you, we've got a new to ProMax 5.0, we've got a fantastic new membrane block. And, you know, basically the idea behind membranes is that you've got a pressure-driven process. You have some membrane made of a polymer, and it's going to have different permeabilities for different components. And what we'd like to do is allow CO2 to pass through the membrane, and you know, keep our natural gas on the retentate side. And this is going to give us a low pressure CO2 product, but you know, it's going to work quite well. And if you compare this to the Ryan Holmes process that we just looked at, you know, membranes have a big advantage of having a tiny footprint. The footprint is going to be much smaller than for, you know, a process where you have 3 big distillation columns of the reboiler and all that. So let's take a look at what membranes just would look like in ProMax. So I'm going to go back to the example that I had up for DEPG, and we're going to use the same feed, but now I've got our membrane block out. And the way this works, it's really easy, it's really intuitive. If I open up this membrane block and I go to the process data tab, I put in some basic information. I put in what the pressure of the retentate is. I put in the flow configuration, I put in the module area, and what I have to do is I have to set up the selectivities. So I've got all of these different selectivities here. For each component in my inlet stream, I've defined a selectivity, and I've set this up using permeability constants, GPUs, in units of GPUs, gas permeability units. And so you can see that for each specific component, I've got a different permeability. So for methane, ethane, etc., I've got these different permeabilities. And then over here for CO2, I've done something a little bit different. I've set the permeability, and I've also set something called a constraint limit type. And so here I've set an upper limit, and I've set an upper limit target of 2%. And what this is going to do is it's going to tell ProMax to design a membrane unit such that I have less than 2% CO2 in the retentate. If I go to process data, you can see that ProMax is telling me that if I've got 200 square meter modules, that I need 25 modules to accomplish that target of 2%. And if I go and I look at the actual block, I can see that the retentate indeed has less than 2%, and the permeate is about 53% CO2. Now, the CO2 in the retentate, it's not exactly 2%, and that's because the module is of a fixed area, right? So the idea here is that if I had 26 modules, or if I had 24 modules, I would be over 2%. With 25 modules, I'm under 2%, so I'm on target. Now, one question you might be asking is, this is kind of a design case, right? I've said, tell me how many modules I need. But what if you have an existing installation where you have, say, 20 modules and you want to know what the performance would be? Well, in that case, you can go to selectivities, and if you just delete that constraint, you can go back to the process data tab, And you can specify how many modules you have. So I could say, well, I've actually got 20 modules. That would correspond to a target area of 4,000 square meters. And now I can come in here, I can click execute block, and I've got 2.8% CO2. So that's not I'm not achieving my 2% goal, but at this point, if I wanted to, I could come in and I could start perhaps reducing the flow rate of feed to see what the maximum throughput of my unit would be. The other question that you might be asking is, where did these permeability constants come from? Now, I supplied all of these permeability constants myself. We do have some built-in permeability constants. If I delete this value for CO2, I could come up here and I could select a membrane type. I might select, for instance, cellulose acetate. And then I could select a reference. There's several different built-in references, and ProMax would automatically tell me what it thinks I should use. And ProMax is telling me that in this reference, the reported permeability is 110. So I could put in 110 and I could perform the calculations like that. But you've got to be pretty careful with these reported permeabilities. They'll give you kind of a very general idea, but if you actually go and talk to a membrane manufacturer or membrane vendor, they'll tell you that the permeabilities are very dependent on temperature. They're even dependent on perhaps composition. So you can kind of get a ballpark idea of what your performance would be using the built-in references in ProMax. But if you're really going to be doing serious work with this block, you'll need to actually have some really good data for your specific membrane. And if your company develops membranes, I mean, the primary users of this block for us generally are people who are actually involved in producing membranes. So, if your organization does that, then you should have those numbers. Otherwise, you may have to get those numbers elsewhere, but it's just something you should think about very, very carefully. I just want to generally caution you against relying too much on the built-in values. And that's basically it for our agenda today. So I hope you enjoyed it. This was just a really quick overview of 4 different carbon capture technologies. And now we've got plenty of time for questions. That was Glenn asking whether you can simulate sweep gas. Yes, absolutely. If you want to add sweep gas to the permeate side to lower the partial pressure, absolutely, you would just go ahead and put it in. You could just take a mixer and have an outlet stream, and then you could add sweep gas like this. And you could just basically mix those 2 streams together and then put them into your membrane. So that's how you would do sweep gas. Can I elaborate more on the water balance in the unit for MDEA sweetening? And yeah, we can take a look at the water balance for MDEA sweetening. Basically, ProMax is a steady state simulator, and that means that what comes in has to be equal to what goes out. In other words, there's no accumulation. Now, we are going to lose water in this process. We're going to have some water leaving in the sweet gas stream, some water leaving in the vent gas stream. Most of our water losses are going to be in the sweet gas stream. That's because we don't have a water wash here. In the stripper, we've got reflux, and that helps keep the losses down. But even if we did have a water wash, we would still have some losses of water. And amine. And so the way that we balance it is we use this makeup blowdown block. And what the makeup blowdown block does, we set the flow rate of our solvent here in the outlet stream. So if I open stream 39, you can see I've got this blue value for the standard liquid volumetric flow. So blue is always telling me that this is the value that I've set in here for the flow rate. We're going to keep that flow rate constant. And then what the makeup block is going to do is it's going to look at what's coming in, and it's going to look at what needs to come out. And if the flow rate of what's coming in is greater than what should come out, it's going to blow down, it's going to purge. If the flow rate of what's coming in is not high enough, it's going to add makeup. And then also it's going to control the composition. So it's going to add amine if it needs to make sure that we hit that target outlet composition that we discussed before. So the key to the water balance in the amine unit is really the makeup blowdown block. I hope that answers the question. If it didn't answer the question and you want more details, just let me know in chat and just be a little bit more specific about what you're looking for. I'll be happy to answer. I've got a question from Manikandan asking about simulating CO2 capture processes. And there's a question, does the licensor solvent hold any additional proprietary data that prevents us from fine-tuning the simulation? If you've got I would say generally no. If you have the correct MDEA and piperazine content in your simulation, you should be able to match what the licensor has. And in fact, new to ProMax 5.0, we've got a concept called the mixed species. And now we're actually able to include some of these licensed solvents in ProMax. If I open up the active environment, I'll show you that, for instance, if I go to components, some of the first licensed solvents that we added to ProMax were the Huntsman Jeff Treat line of solvents. And so if I type in Jeff Treat here, I can see I've got all of these different Huntsman Jeff Treat solvents. And so, you know, if I'm using the activated MDEA version of Jeff Treat, this is going to give me very good results that are confirmed by the licensor. We've also got the Dow solvents in ProMax now, and we're currently working to get some of the other licensor solvents in. But, you know, just generally speaking, I would say that if you've got the correct concentrations of the correct amines present, you should get the correct results in ProMax. And as far as I understand it, the way that we've actually implemented those mixed species, when you use Jeff Treat, when you use that, you know, Jeff Treat or Dow-Euchersol solvent in ProMax, under the hood, behind the scenes, in the code, it's actually just blending together the two amines. It's just that the licensor has told us what that composition is. There's a question about the rule of thumb for how much water wash is required for limiting CO2 slip. And I don't, as far as I'm concerned, I think that the water wash, now, when I hear water wash, I'm thinking of a water wash that's on top of the absorber column. So sometimes you'll have a few additional trays above the lean amine feed where you have water. That flow rate of water, it's nice to set it equal to the necessary water makeup rate, because that way you don't have to purge. But I don't think that it really does very much in terms of CO2 absorption. You're not really going to absorb very much CO2 in just pure water from a water wash. So I would say that in terms of limiting CO2 slip, the water wash is not particularly relevant. I hope I understood the question correctly. We've got a question. What lean amine loading would you typically regenerate the rich MDEA to? Typical lean amine loading is around 0.01. Yeah, that's pretty typical, I would say. 0.01 or less is very common for MDEA. You don't want to obviously over regenerate. I'd say that, you know, you need to really, when you look at MDEA systems, it's kind of hard to give you one piece of advice and say, this is the lean loading that you should use. You really have to look at these systems holistically and think about how the absorber and regenerator operate in tandem. So, like, if I was looking at what the appropriate lean loading would be, one thing that I would do is I would look and see, am I lean and pinched? I would create a lean approach in the MDEA absorber, and I would look at the lean approach. And if the lean approach was near 90%, indicating that I was in a lean and pinch situation, you know, that would tell me that my sweet gas purity was being limited by my lean loading. And then what I would do is I would ask myself, is that actually a problem? If I was very, very far away from the specification, if I was very easily meeting the specification, maybe I would actually say I'm okay with being lean and pinched. But if I was right on the border where, you know, I was lean and pinched and my sweet gas had, let's say, we'll use H2S as an example. Let's say that I had, 4 ppm as my specification, and I was at 3% H2S, and I found that I was lean and pinched. That's where I would start thinking about increasing my reboiler duty and reducing my lean loading. Really common rule of thumb is to, now this is in English units unfortunately, but it's just really nice. We say for MDEA, and this is pure MDEA without piperazine, we tend to say like 1 pound of steam per gallon of solvent, and you can convert that to metric units. If you think about it, a gallon is about 4 liters, and a pound is about half a kilo. So it's about that would be what, about 8. I confused myself, but anyway, you can do the conversion. But yeah, I guess the point is, in terms of setting the lean loading, start with some of the rules of thumb for the duty, or like 0.01 is a good starting point, and then look at the system holistically and figure out where you need to go. So there's a question about what models are used to calculate the chemical enhancement, rigorous or HADA. I think the enhancement factor, let's take a look at the help and see if we can find anything about the enhancement factor in the help. I don't want to give you the wrong answer. And this is a good demonstration of how in-depth we tend to go in the ProMax help file. So we'll go to File, ProMax help, and I'm going to type in under search, or I'm going to go to index, and I'm going to search for enhancement factor, and I don't see anything about the enhancement factor here. So I'm going to search for HADA here. And it looks like there is a little bit of information about what we're doing. So we've got this note down here. We say in the case of gas-liquid reactions, use your reactions are considered using bulk liquid phase. Consider estimating the enhancement factor via the HADA number. And then let's try searching for enhancement factor. Sorry to go off in the weeds here, but maybe you'll find it useful to see how, I would approach looking for something I'm not totally sure of what the answer is. Okay, so looks like I'm not finding too much information about how the enhancement factor is calculated. Let's open up the column. Yeah, in terms of that enhancement factor, I'm not sure. We're going to have to get back to you on that. We'll just make a note, and we'll ask our development engineer who's responsible for this, and we'll get you guys an answer on that. I'm not sure what models we use to calculate the chemical enhancement. So Tomasz has a question. Can you replace DGA with activated MDEA to increase the capacity of the CO2 removal plant? Maybe. That would be a good thing to try out in ProMax, I would say. Like I said, there's some things you've got to think about, like the different heats of reaction, the different corrosions, but I would say generally, yes, you could probably replace DGA with activated MDEA. That's an interesting question, Patrick. So Patrick asked, is it possible to adjust the solubility of components in DEPG? Which components? Like the hydrocarbons, or what are you thinking about, Patrick? So if I go to my environment, I've got my Penn-Robinson polar environment here. If I go to my binary interactions, I've got binary interactions available to me for my regular Penn-Robinson class and for my Penn-Robinson polar equation of state class. And here, if I look at this table, and It's not letting me scroll. There we go. You can see that I've got the ability to actually come in here and manipulate binary interaction parameters myself if I want to. So if you've got data that you'd like to match, you certainly could adjust the solubilities by adjusting the binaries. And that's something that we could probably also help you with. So the answer, Patrick, to that is yes. So Salman's question, what should you use for capturing CO2, MDEA or DEA? I would say MDEA, activated MDEA is probably the most popular these days. And again, we had that slide where we discussed why MDEA is so popular. It's because it's not particularly corrosive. You can use it in high concentrations, which means that you have low reboiler duties. It has a low heat of reaction with CO2, which, that can become important. I have seen cases where you have piperazine present and the heat of reaction gets high, but the heat of reaction is high with DEA as well. So just generally speaking, I would say for CO2 capture, activated MDEA is going to be preferable to DEA. Tomasz has a question. Do you compare the actual results versus calculated results using membrane simulation in ProMax? So the trick with membrane is that you have to know the permeability. Honestly, if you go to a membrane vendor and you ask them what the permeabilities of the membrane are, they're probably not going to tell you. So have I personally done it myself? No. However, we've got several customers who are membrane vendors who produce membranes, and they have given us very, very good feedback about the tool. And Katrina's actually answering in chat that she's done it herself with real permeabilities and gotten good results as well. So yeah, the membrane block gives really, really good results. But it's like anything else in simulation. There's the expression garbage in, garbage out. If you've got the correct permeability and the correct feed, then the results that you're going to get are going to be very, very, very good. So Hussein has asked, is MDEA more selective towards CO2 or H2S? So MDEA, methyl diethanolamine, it's selective towards H2S. So we say that it slips CO2. And again, that's the reason that we have activated MDEA, because in cases where we don't want to slip CO2, where we want to capture all of the CO2, we need to add an additive like piperazine to capture the rest of that CO2. So yeah, when we talk about MDEA being selective, it's selective towards H2S, it slips CO2. Well, the reason Hussein that we wouldn't use DEA, I mean, DEA, it's as a secondary amine, it's more corrosive than MDEA. It has a higher heat of reaction. It's more difficult to regenerate. And so you can end up basically having a more efficient process if you use MDEA. So when I say more efficient, I mean perhaps smaller columns and a lower reboiler duty. You can oftentimes, perhaps typically we can say, have a better design process if you use MDEA with just the right amount of piperazine to get your CO2 absorption to where it needs to be. Now, I'm not going to tell you that activated MDEA is always going to be better than DEA. There are still some DEA units out there operating, and there are sometimes new DEA units being installed. But I mean, I would say for me, if I think about like what's really common right now for like a new unit, activated MDEA is kind of the go-to. It's kind of the default if you need to do this. So Mani Kandan has asked for a few examples of feed stream sources for CO2 recovery processes. I mean, there's lots of places where you might need to recover CO2, right? Different feeds could be syngas. Syngas has lots of CO2. Natural gas can have lots of CO2, especially if you think about maybe like a reservoir where you're using CO2 for enhanced oil recovery, right? You're going to have lots and lots of CO2 that comes out of the ground with the oil if you're using CO2. If you're injecting CO2 in the reservoir for EOR, you're going to have to deal with that CO2 later on. Flue gas is an obvious one to think about, power plant flue gas. And then perhaps biogas would have CO2. I'm not really sure on that one, but you know, there's lots of different places that you could encounter CO2 in a gas stream. There's a question about whether MDEA or DEA is cheaper or more available. In terms of the prices, to be honest with you, I have no idea. But in terms of availability, I would guess just based on popularity and the number of units that are out there, I think it's probably going to be easier to buy MDEA because it's just more popular. But I don't really know. That's kind of outside of my realm of expertise. In terms of calculating millimeters per year of corrosion based on metallurgy, that's not possible in ProMax yet. I think that'd be a great feature to add in the future. Okay, so in terms of CapEx and OpEx, you know, in terms of CapEx, ProMax has very good equipment sizing capabilities. So for instance, in an amine absorber, we can tell you exactly how big it needs to be for a given fraction flooding. And obviously in terms of OpEx, we're going to tell you what your utility requirements are. But we don't have anything built in terms of cost estimating. So if you're looking for actual, you know, dollars, you'll have to use an additional reference to get that. Can this process and calculations also be used at very low gas pressure to remove CO2? Activated MDEA, I think at very, very low gas pressures, I'm not sure how activated MDEA would perform. It's something that you'd probably have to try. I mean, it would depend on the partial pressure of CO2 in your, even if it's low pressure, it's still going to depend, it would still depend on the partial pressure, I suppose, and how much CO2 you needed to remove. There are some new, for flue gas capture, I mean, usually what we hear about flue gas capture in the literature is the use of primary amines. And so previously it was always MEA. And nowadays there are some like next generation primary amine solvents, like Mitsubishi has one called KS1, Shell has one called CanSolve. And those are also primary amines. Activated MDEA for flue gas capture, I'm not sure. I don't know. What do you think, Katerina? I know you're in the chat. Okay, so the question is, have you seen activated MDEA being used in any kind of flue gas capture, or do you think that the partial pressure in flue gas capture would just be too low for activated MDEA? You know, one of the things about ProMax that's nice is, I mean, we could just try it. You know, you could just do a quick simulation. Here we've got about, here we were at a pressure of 55 bar in the example that I showed. Okay, what's the minimum gas pressure that we can use activated MDEA at? Okay, that's going to, one of the things that's going to depend on the maximum gas pressure, it's going to depend not so much on what the pressure of the gas is, but what the partial pressure of the CO2 is, right? That's what's really, really important. And here's what I would suggest. Instead of trying to just, you know, tell you a rule of thumb, ProMax will just tell you, right? So the best way to find answers to questions like this are to just simulate it in ProMax. So yeah, I think that really I'd prefer to like kind of take a step back and say, you know, I don't necessarily want to give you like a prescriptive answer to these are the conditions that you can use activated MDEA for carbon capture. I'd say just if you've got an idea, the great thing about a process simulator like ProMax is you can just try it, and you'll kind of have an idea in a matter of minutes. Can you use ProMax to determine the weeping point? Well, let's take a look. I'll show you what we've got in terms of column hydraulics, okay? So if I open up this amine absorber, if I go here to the general tab, you can see that we're calculating the diameter right now based on a specific fraction flooding. But if I wanted to actually fix the fraction flooding, I could do that too. So this column had about 1.1 meter diameter. And if I execute the column now, basically the ProMax is going to report to me the fraction flooding. So I'm at 70% right now, so that should be pretty safe and pretty far away from, weeping and dumping. And then if I want to look at some additional information, I can click here in tray, and I've also got the flooding as calculated per the Koch glitch equation 13. And I can also get some details about my downcomer. So I've got the downcomer flooding and the downcomer froth back up here. I've got some details about pressure drop here, what the expected pressure drop would be. And then some information about just fine details like about the froth model. So we don't specifically report anything, we don't specifically report the weeping or dumping point, but I think that you could probably get a pretty close idea of whether your column was operating in a reasonable range from what we do offer, the fraction flooding and the downcomer flooding. There's a question, does ProMax adjust the solubility of gases in DEPG when the amount of heavy components and water is building up in the physical solvent? Yes. So the solubilities should still be correct even as those heavy components accumulate. Definitely. And then, okay, well, it's 1 o'clock. We had a great Q&A session. I really appreciate all the interest. So thank you guys for joining us today. And see you at the next one, everybody. Bye.